Okay, hi everybody. You need to turn yours on too. I'm Jeremy. This is Leslie. Welcome to the University of San Francisco Data Institute. We're very grateful that they've been able to provide us with this space. And we're particularly grateful to be joined by Leslie Smith, who I'm sure needs no introduction. As well as Leslie, we're also joined by people through the live stream and the recording. So thank you so much, Leslie, for both coming here and agreeing to let us share this more widely. Welcome to San Francisco.
Thank you very much. I appreciate the opportunity. In case people here don't know, even though Jeremy has talked about me very nicely, I've never met him before. The first time I met him was just about an hour ago. And so I waited, I didn't want to break the surprise, but I waited till now to actually be able to say what's really on my mind. And that is that I'm really very full of a lot of gratitude to you.
To me?
To you, absolutely, because you've taken my ideas, you have publicized them. Now I go to conferences and people actually talk to me.
Yeah, so it's funny.
Who knew?
It's funny because I don't have an academic background myself, and so when I started trying to dig deeper into the academic literature of deep learning, I kind of didn't really know who famous names and not famous names were, so I kind of just picked things that looked interesting. And then I found this paper by somebody who was as unknown to me as anybody else in the field, and read it, which was the cyclical learning rate paper, and found it really interesting. And it also reminded me of stuff that I did 20 plus years ago when I first was playing with neural networks, and I kept noticing, like, I wrote something in Delphi, which was an old Windows programming environment, to like let me, from time to time, like I could press a button and it would make all the weights like bounce a little bit, and I found it helped me to get better results. So when I read your paper, I thought, that's kind of what was going on 20 years ago. So then I actually kind of looked you up to find out, like, who is this person and what else has he written about. And I kind of thought, I don't know who this person is. Like, nobody was talking about you. And I thought, that's crazy. So it's like, yeah, everybody, you got to check out this guy, Leslie Smith. And we talked about you in the MOOC. And I think I called you the most underappreciated researcher in the field, which is definitely now not the case. A lot of people are aware of your fantastic work. So I'm really glad you put it out there and made it available. So you kind of were looking at how can you change different parameters as you train, and so the cyclical learning rates paper in particular was about changing the learning rate while you train. And so I guess there's a long history of changing the learning rate downwards, particularly in big steps downwards, but you added two things, I guess. One was to gradually increase it, and the other was to, particularly with the one cycle paper that followed up, to change the momentum as well. So I guess I was interested to kind of know a bit about the background, like, why is this a problem that you're interested in solving, and then where did the kind of the intuition or the idea come about of like gradually increasing the learning rate and also changing the momentum at the same time?
So about 4 or 5 years ago, I was annoyed. Sorry. What happened is that it was well known that learning rates were the most important hyperparameter to tune. Mm-hmm. And if it was too large, the training would diverge. If it was too small, not only train slowly, but you would train to a suboptimal solution. You had to get it just right. And how do you find the optimal learning rate was generally done by grid search or even random search. But you would make many runs at different values, and you pick the one that seemed to do the best.
Which takes a lot of powerful computers and a lot of time.
A lot of time, exactly. So I was annoyed. I said, well, it's got to be a better way. I thought, well, in horseshoes, close counts. So originally my thought was, what if instead of trying to get an exact, trying to get the optimal, what if we are close enough? So I came up with the idea of a bound, an upper bound, lower bound, and just let it go in between the two bounds, and that's where cyclical learning rates came out. And it seemed to work because all my experiments showed that it worked as well as if you had done a grid search and you found the optimal value.
So I mean that's already pretty interesting to me, because there's a lot of people who are interested in this field of AutoML, and AutoML still tends to mean basically doing a grid search, but maybe doing it a little bit more efficiently by kind of deciding which parts of the grid to look at next. Google has this whole product they call AutoML, where they say, like, well, you get to use our massive data center to do that grid search faster, and that's going to empower data scientists. I think you and I both have we just met, but we seem to have a kind of a common belief here that getting a computer to do a massive grid search, even if slightly more efficiently, isn't really the right approach, but actually that there are some more correct ways to train a neural net, and you're kind of searching for those heuristics and rules and algorithms rather than throwing more computers at the problem.
I tend to prefer, I guess in some ways, I look to make it easier for the masses of people to do it, because if I can make it easier for a lot of people from a practical perspective, that's something that kind of appeals to me.
Yeah, well, I mean, me too, but why is that appealing to you?
Well, because it's not always obvious how to do that. And I tend to be a curious person, and I like to kind of think about, well, if I wanted to make it simpler, like in terms of finding an optimal learning rate, how would I do it? And then it's just one thing seems to lead to another. So like the learning rate finding, I call it one of my trains test, I came out of doing one cycle. And one cycle came out of trying to make things easier.
So just to clarify, so the learning rate finder or the range test is this idea that you quite quickly in the fast.ai library, we just do it 100 batches, not 100 epochs, but 100 batches. So it takes a few seconds. Run a batch at a time through, starting at a very, very low learning rate, smaller than you would expect to ever need, and gradually increasing up to a higher learning rate than you expect could possibly be acceptable. And at some point, the loss will shoot off to infinity, and you plot all the losses along the way, and you kind of pick a learning rate where it was decreasing fairly quickly, which is, like, when you say it, it's kind of an obvious thing to do, but until a year or two ago, no one had done it. So, it definitely saves. It's actually one of the first things we teach in lesson 1, the introduction to deep learning, is to do that, because as you say, it's such an important hyperparameter.
Right. And from a practical standpoint, if you can do one partial run, 100 batches, it makes it pretty easy. It makes it accessible. So accessibility is one of the things that kind of motivates me. Right now, one of the areas of research that I'm pursuing is minimizing the size of the training data.
So I guess this is a common theme. So accessibility is a word I use a lot as well. It's a word that often seems to be misused, but I guess when we say accessibility, we just mean we want more people to be able to use deep learning to help them do whatever they're doing. So if that means it needs to be cheaper, it needs to be faster, it needs to be easier. And if you kind of have those things, then that means more people can use it. So cheaper, faster, easier. So in the cheaper side, well, also I guess being able to use less data, not only is it cheaper, but it also means that more problems can be solved, because you're not limited, constrained to only problems where you have really big data sets. So being able to use smaller data sets is certainly interesting. So now this is not something you particularly published about. This is more recent research.
This is more recent research.
So give us a sneak peek.
What?
Give us a sneak peek. What have you found?
Well, first I'll say why I got into it is because that's what I got funding to do.
Okay.
And
how do you get funding? So you work at a military research lab, top secret base patrolled by aliens or something?
Unfortunately, but I tend to prefer to do everything on unclassified domain. I like publishing. I like getting my work out to lots of people. But unfortunately, the job requires having funding. If you don't have funding, then I guess I could work without getting paid. But even that only goes so far. So you have to be able to sell the things you want to do to people who have money to pay for. And if you think about it, deep learning was built on three pillars. Everybody says it's been for years. One is lots of training data, and two is lots of hardware, and three are the new algorithms. Now, which of those three are really the barriers in terms of, computers are getting faster, but the training data, I think, is a barrier.
Yeah, particularly one of my big interests is medicine. And particularly in medicine, I'm very interested in pediatrics. And kids' diseases are weird, they present differently, different age kids. So kind of every data set has different meanings. That kids get rare diseases. There's just a huge bunch of, if you want to, figure out how to help diagnose and treat kids, you're constantly working in a low data environment. So you don't want to rule out whole parts of the world and say, well, we're not going to work on helping get kids better. So that's an example of where using less data is increasing accessibility.
Right. No, that's a good example. And even I was at the ML conference earlier today, and at the ML conference, people will come up to me, which is a new experience, and they would say, I'm working with 30 examples, especially in the medical field, for example, training data is very limited. So this seems like a good place to make a significant strides.
Absolutely. And actually, the work that I did with Sebastian Ruder earlier in the year on NLP was very much about that as well. It was basically transfer learning is such a great way to reduce the need for the amount of data. Can we make that work, for reasonably small corpuses of text? And we found, actually Sebastian did a great experiment where he tried different sizes of the IMDb data set subsamples ranging from all the way down to 100 reviews and got close to state-of-the-art accuracy, comparing it to what would have required before 25,000 reviews. And so this is one of those places where we can now say, hey, maybe if you're, in fact, one of our students just did this, he's a lawyer, or that's his background as a lawyer, and he used the algorithm to classify legal texts. And it's great if you can classify a few by hand and then let the computer do the rest, I guess. Yeah. So anyway, so tell us, what's your new kind of direction for this problem?
Okay, so what's my new kind of direction? Actually, what I'm working on, one of the things I'm working on a lot of things. I've got a dozen things going on. So I'm going to say one of them is the problem of incremental learning. What I mean by that is we're going to start with the case where, the base case, we have lots of training data, and we're going to train a network. But when it's being used in a production environment, we may get samples that are over classes that it wasn't trained on. So we train on n classes, but we get something that shows up that's n plus 1. So we need to be able to do two things, or n plus 2 or 5 or whatever. We need to first of all be able to have that network recognize that it's not one of the classes we trained on. And then I've got an architecture where we take the novel ones and we use this whole field that started called few-shot learning, if you're familiar with it.
Absolutely.
Okay, so then to take the cases where we only have one or just a few examples, and then use a second network that could be pre-trained with a large base. We have a large base data set, so we can pre-train it to be able to handle few-shot learning. and then train it to on the one or few samples we have to recognize the extra classes. So it's a
So it's kind of a transfer learning exercise in a sense.
How so?
Because you're starting with a model that's been trained on lots of data, and you're kind of trying to create this submodel or derived model that's going to work on this new class or this smaller amount of data.
So
leveraging the training that you already did.
So the way few-shot learning generally is done, there are, I guess, some of the major techniques are like MAML and prototypical networks. The way it's generally done is that you have a certain number of classes that you train on, and where there is data that you can train it to do tasks, and each task is a few-shot learning task. You have like maybe 5 classes. You may have one or a few members per class. So you have a lot of data to do this training initially. So I'm doing the same thing here. So it's not really transfer learning, but it's really falls closer to the realm of what they generally do in few-shot learning.
Are you familiar with a paper called Devise by Andrea Fromm? That's one of my favorite approaches to few-shot learning, which I really like. And Andrea Fromm is definitely, one of these people who is not nearly as well known as she should be. So her idea was to say, let's not make it dependent, as we were on district and others, let's not make it dependent variable a bunch of categories if we're doing classification. Let's instead represent them as a distributed continuous representation. And so the obvious way to do that is to take a word vector, like a glove or a word vector. And then you just train a convnet in the usual way, but instead of your dependent variable being one hot encoded, variable that you compare with cross entropy, your dependent variable is a word vector. And the nice thing is then that if you come across an image that is of a breed of monkey you haven't seen before, it's still going to recognize that word, produce a word vector that says it's a breed of monkey with these characteristics. And then it's just a simple case of doing a k-nearest neighbors, to find the word vector that's similar. So I think that's a really interesting approach to few-shot learning, is to kind of say, yeah, hey, if the dependent variable isn't a class anymore, but is actually a continuous thing, then it doesn't even have to be few-shot learning anymore, which I love.
So I have one of the ideas that I'm working on, very closely related to what you were just talking about in terms of, so with the Devise paper, they basically are using a word vector as the labeler.
Exactly.
Right. So one of the techniques I mentioned that is kind of one of the big techniques in few-shot learning is called prototypical networks, where for each class they take an embedding vector and they say this is a prototype, and they try to do clustering.
Right.
And that's kind of how that works. So I had the idea that what if instead of taking one of the class vectors as a prototype, what if we did what I'm calling semantic prototypes? So that we take the label of the class and we make a semantic embedding vector from that. And then we use that as a prototype. And what the prototypical networks try to do is bring all members of that class close to the prototype. Now, I'm hoping, actually the truth is it's so new, I have jobs running now as we sit here to see if this idea even works. And I'm not ashamed to tell you that most of my ideas don't work.
Yeah, I wanted to talk a bit about that process, the process of doing research. I find, so I have a big room here at USF that I leave, particularly, well, not this one, but where I do my work, which you saw this before, which, as you saw, it's full of people, and the people that are in it are just random people who happen to be taking the course, and I let anybody join in and hang out. And I find, and so often when I'm doing my work, I'll project it on the big screen so people can see. And the most common feedback I get is, wow, Jeremy, I didn't realize you had no idea what you're doing either. 99% of the time I'm doing stupid things that I then throw away, or, totally, or I run an experiment that I totally stuffed up or whatever. So by the time somebody sees my YouTube video, they've seen my months of work, of which I kept for like the 5 minutes that actually worked. So yeah, I mean, like, what's your process of like? Okay, so I feel like you've given us a sense of how you come up with an experiment, which I like. It's rather than like, here's something that academics are interested in and you can publish a paper about, but it's actually, here's something which is going to be useful for people. And then you come up with ideas of like from intuition around like these things might work. How do you then like, kind of, how long do you dig into an area for? How do you decide when it might be working? And then like, how do you kind of graduate it to the next level of like, oh, I like this, I'll take it further. What's your kind of process there? And how do you stick with it? How do you avoid getting, disappointed by all the failures that we all have along the way?
So those are a lot of questions. I'm actually going to start with something that you made me think of earlier. There's a book I read years ago by Richard Hamming, The Art of Doing Science and Engineering.
Right.
And the quote I like there is, in science, if you know what you're doing it wrong. So the fact that they say that you put the stuff up and you don't know what you're doing, that means you're doing science. So that's actually a good thing. Now, how I do science, I guess the best way to start is I have beliefs, so I have an intuition.
Right.
How I think everything works. So I guess I'm very opinionated.
And that's already different to what a lot of people think, because a lot of people come from a background of more like, computer science or math course where it's a whole lot of algebraic symbol manipulation, and a lot of people come out of university thinking that's how you do science, is you're manipulating algebraic symbols. But yeah, everybody I know that does breakthrough research actually tends to start with intuition, not with math.
Right. So generally what I like to do, I do a lot of experimentation. So usually what I say, well, I think, based on my beliefs, based on my intuition, I think that if I do this is what will happen. I also will make myself thought experiments. Why is, like I was showing you earlier in terms of weight decay, when the learning rate changes, why do we get this jump in accuracy? So I say, well, I think it's because of whatever, and I test it. So, people, I give a talk and people will ask me questions. What do you think will happen if? And I say, well, I think this will happen, but I could be totally wrong. Matter of fact, I'm totally wrong more than I'm right. Well, a lot more than I'm right, but don't tell me. So I actually will try and actually write things down. Matter of fact, I have a notebook. Also, my notebook is full of all the gems. So I have a notebook and I write things down and I say what I think things are going to do, and then I test it. And if it's different than what I think, I'll be curious about it. And so that curiosity drives me a lot.
I would say also, like, I like to kind of keep an eye on seeing, like, the most effective people I know, what are the kind of things I keep seeing, and like a notebook, whether it be paper or physical, that they're constantly writing in is a very common theme as well. I feel like people who are really effective realize that we want to offload as much as possible from our brains and that we'll forget stuff. And so just, jotting stuff down seems like a particularly powerful tool that not enough people use.
Right. No, it's very good, especially when I'm trying to do like a dozen different things. And in the kind of experiments I do, they take time. So I set off experiments and then I go give an interview or whatever, but I do other things. So to keep track of things is also, fun. But in terms of the science, I think the science is a lot of thinking, because when you get results that you don't understand, you need to pay attention to that. One of my best, I think the best things come out of when I look at something and I say, well, that's weird.
Yeah.
And then that's how you stay motivated. Well, I want to know what's behind it, what's going on.
Yeah.
So it kind of keeps me looking at it. I try many different things.
Yeah, I mean, like the famous discovery of the they call the inert gases and the elements was somebody noticed a bubble in a beaker, and it's like, that's weird.
Right.
And I guess it's like, but being able to recognize that something's weird and it's not, well, it's not necessarily just because you did something dumb, requires a certain level of craftsmanship. Like you need to actually, like a lot of the things you're describing require you actually being pretty decent at writing code, because you need to be able to like implement the experiments you're describing, and you need to like know that at least a reasonable amount of the time when you write the code that you think you're writing, it actually is what you thought you wrote, and if something's weird, then that's potentially an interesting research artifact. So it seems like being able to code effectively is something that you're finding important for the kind of experiments you're doing too.
So I try, I don't consider myself a terrific coder. Don't tell my boss. But I try to be flexible enough so I can work on like any framework. So one of the things I do is when I read a paper that I find interesting and the authors have made the code available to replicate it, is it'll go in, I have a folder, I have lots of folders, see there's some of them. And I have a folder on code that I'd like to. Those ones folders. I do a lot of them. My folder.
This is what gets carried to talks.
So anyway, I have a folder on code I'd like to download and just replicate.
Yeah.
And so I have a little bit of a goal to try and experiment with different people's codes to see how.
And how does that work for you? Do you kind of just like grab it from GitHub and try to run it as is, or you try and like re-implement it yourself?
No, I don't have enough time to do the start from scratch kind of thing.
Mm-hmm.
Sometimes, I mean, often I come to papers that I really like, but they don't make the code available, and I'll never get around to replicating the work, no matter how much.
So when you grab that code and you're going to run it, I mean, the thing that gets value, I guess, is when you look at the inputs and the outputs. So, like, is that kind of your next step? Is then to like try some different inputs, or you kind of print out some intermediate values, or how do you kind of learn from that process of looking at other people's code?
Okay, so it depends. I want to get experience with as many things as I can, and if one thing can lead to another, because I guess stream of consciousness a bit, then I'll try different things and experiment. Say, what would happen if? Because I do a lot of what would happen if. And
right.
One of the things you said in terms of being able to is if you write things down. If before you do the experiment, you write down what you think is going to happen, and then after it happens, you check. Because if you don't write it down, so well, I think this is going to happen, and then something else happens, and you ignore it because you hadn't written it down.
Right. Or you kind of post hoc justify it, like, oh yeah, I always knew it was going to be like that. Yeah. Exactly. No, I mean, so this is like the thing we kind of keep hammering when we teach the course every week is to say to people, write code, right? And when you write the code, look what's going into it, look what's coming out of it, try putting different things into it, try looking what comes out of it in different ways. That's how you get the level of intuition that you have to then be able to say, like, what if, or even more interestingly, that's odd. Because you can't say that's odd if you haven't seen 100, trainings already.
I suppose when you start off, you might say everything, that's odd.
Right,
but
which is fine.
Then you learn, that's how you get, see, you start from your intuition, but your intuition, if you're new at the game, will be nil.
Yeah.
So everything's odd, so you should be looking at everything until you reach a point, because the purpose of science is understanding.
Yeah.
That's my perspective.
And this is another reason I kind of try to push people away from too much algebraic symbol manipulation, particularly in the early years of their development, because for most people at least, that's not a great way of getting a deep intuition of what's going on. The intuition kind of comes from running experiments and seeing what happens.
So I think there are two kinds of people in the world. Well, this binary, maybe 10 kinds of people. So there are people, who go to the top universities and they get their PhDs and et cetera, and they're very theoretically oriented. And I'm not one of those people. But I like collaborating with those kinds of people because they complement the things that I do. I have a little, though I like doing the more fundamental research, I have a practical bent to kind of like you do too.
Can I ask a bit about that, Leslie, about that background? So I don't know anything about your background. Did you come here often? So did you do a kind of a computer science PhD at some point? Was it in kind of neural networks? Have you been in this field for a long time?
No, actually not. I'm not as young as I look. That's dangerous. So I got my PhD 40 years ago. That's also dangerous. And it was in quantum chemistry. So
that sounds so hardcore.
It's more computational physics than it was anything else. But there have been a lot of revolutions over the years. I even tried, actually this kind of cute, I even tried to start my own business, which was a disaster. I learned that I couldn't sell $20 bills for $5 standing on the street corner. So that didn't go so well. But science I like. So when I started at NRL, 15 years ago?
That's the Naval Research
Laboratory. I was doing computer vision. And so my background is actually more in the computer vision area. And then about 2013, took notice of...
So you were doing all the kind of hog and sift and...
I was doing more sparse representation, if you're familiar with
okay, like those kind of dictionary...
Yeah, dictionary learning, which is a little bit ML, machine learning oriented. So I was doing more of that kind of thing. But I took notice of deep learning, and it just struck a chord with me. And
so that was 2013. You kind of
so about 2013 I started getting into it, and I was fortunate. I had a boss who just kind of left me alone. I was being paid to do surveillance, and I wasn't doing surveillance. I was doing deep learning. And he let me...
Luckily, nobody noticed because the Office of Surveillance doesn't do a good job of surveilling their own stuff.
Smart surveillance is what the project was. But I got smart in other ways. And, one thing just led to another.
So let me just mention, we have can you hold up the microphone? We have a microphone here. So if you have a question, wander on over. The only reason I'd rather you came here than send the microphone out to you is so that the people can hear. But don't be shy if you have a question, or if you have a question online, you can pop it in the chat.
So I can ask them questions.
You can ask me questions.
So why don't you tell me about how you got? You're so famous now, and you're like a celebrity.
Nerd famous.
How did you go from you were Kaggle, I believe, and what's your background? How did you go?
I did not do quantum chemistry. I didn't even really turn up to university. I started full-time work when I was 18. Like Francisco, who's behind the microphone here, I went into management consulting when I was 18. So I spent 10 years, studying the competitive advantage of companies and how come some companies are more successful than others and what makes CEOs successful, or what kind of organizational structures are more efficient and so forth. And
is there an answer to those questions?
There are large areas of academia who study nothing but that and have done for many decades. So there's certainly attempts at answers to those questions that are at least as controversial as the question of do sharp minima generalize or whatever? There are questions and answers that people partially agree on or not. Anyway, because I started that a lot younger than everybody I was working with, I could not rely on my expertise because I didn't have any. So I quickly realized that the only way for me to be successful was to do a data analysis approach, which basically nobody else in strategy consulting at that time that I knew was doing. So, so I tried to teach myself, because I didn't have any academic background, I tried to teach myself, how to create a database in Microsoft Access or use Visual Basic in Excel or whatever. And I started learning about things like linear programming and optimization and regression. And I was thrilled to discover that this different angle to solving business problems, people really liked it. And so I did really well in management consulting, and I progressed quickly and got to a point where I wanted to start my own company. And so I started a couple of companies, and I just kept on this approach of like using a data-driven approach to everything. And so I guess I never thought of myself as somebody who was any good at data analysis. It was just something I happened to do. So Kaggle was interesting, right? Because after I sold a couple of companies and I had time on my hands, I spent some time, I did a Kaggle competition. And I did it because I wanted to learn how to be a proper data analyst person. And apparently, all the cool kids used R, and I've been playing around with predecessor to R, S+ a bit in my work. And I went to an R meetup and told people I wanted to try a Kaggle competition. And and I tried it to kind of see if I could not come last. And and I won it. And like was deeply surprising to me because the other people in the competition were like PhDs and whatnot, who I always was terrified of, totally intimidated. And so to discover that a bit of common sense, and ability to write code can actually beat econometrics professors at an econometrics competition was really heartening. And it kind of changed my direction. It made me think, there's something in the world I am apparently really good at, so I should focus on it. So since then, I've been focusing on using machine learning, getting better at it, and getting better at kind of applications of it. So I started this company called Analytic, which was the first company to try and use deep learning for medical diagnosis, at least to focus on it. And so that was really interesting and went pretty well. And then, I guess I realized deep learning in particular seems to be valuable for so many things. Working on just one thing was never quite going to cut it for me.
So you like doing many things at once?
Or I kind of wanted to help lots of other people do many things at once. So that's why we started fast.ai, was to kind of say, like, let's build software to make deep learning easier. Let's teach people how to like do deep learning in an easy way. Let's do research into how to make deep learning easier, and then like have, then I don't have to do any real work. I can just have other people do the work,
Jeremy, we have a good question.
Okay, great. Hit us, Francisco, with your question.
So this is for Leslie, I think. How do you know when to stop a line of inquiry? Is there always something worthwhile when you notice something is odd? Or are there times that you just give up?
So the answer is yes. I suppose that's not sufficient. I tend to be a little bit on the persistent side. And so I'll give an example. We're talking about the device paper a little bit earlier. So this summer I had some summer interns came to the lab and was working with me. And I had this idea of using embedded vectors in terms of labels then, and thought that it might help in terms of new classes, because the new class, the embedded vectors would be similar, and hence the features that the network learned were, in theory, I thought maybe, or in intuition, maybe not theory, but in intuition, I thought that it would allow it to learn new classes more easily. So it was related to this incremental learning. So we worked on it for actually several weeks, and it wasn't working so well because it seems training a network with one-hot labels and softmax works better, because the semantic label, one-hot labels are orthogonal. Does that make sense?
Yeah, absolutely.
Mm-hmm. And the semantic vectors are not orthogonal. So the dirty little secret behind the device paper It doesn't work as well. I guess they kind of have that this trying to say it as well, because your orthogonal vectors will get a better performance than using semantic labels. So,
I mean, just to clarify, I guess there are plenty of things the device approach does better than the classic, one-hot encoding approach. But yeah, if you judge it on the same accuracy metric as classic ImageNet models, it won't have the same accuracy.
So we were trying to see what would happen when we introduce new classes, but it turned out that because of the disadvantage, we weren't able to achieve as high an accuracy.
That's interesting, because like the things that the device paper does better than the classic models tends to be more like making more sensible mistakes, for example, or kind of predicting things in the right general area.
So intuitively, I thought that it would work. And then we reached the point where we couldn't get better results. So to answer your question is, when I kind of reach a roadblock and I can't think of what to do that will make it work, we stop. So we actually stopped and we changed it to a different, I got the students working on a different problem. Actually, it's kind of fun. I said to the students at this point, they've been there for 5-6 weeks, let's brainstorm together and see what we can come up that would be interesting to work on. And we did. We came up with some, we all threw out ideas and we came up with something that was.
I mean, I suspect there's probably a lot of things people, like, I think people should take your idea and maybe some people could run with it from there. Because to me, this question of like, to me, this is one of those, that's odd moments. It's like, oh, that's interesting that, predicting vectors that are actually pretty close to each other for concepts that are conceptually close to each other doesn't seem to work as well for certain kinds of tasks than predicting orthogonal things, even though those things are pretty close. To me, that's odd moment. And like, it's particularly odd because there's a lot of situations I've seen where the kind of conceptually the opposite holds true. So for example, in medicine, when rather than using a one-hot vector, instead we'll have like an n-hot vector saying like this, it's not just this illness is like some combination of where it is and what it is and how long it's been there for, but it's like, n labels representing all different features of the diagnosis. And that tends to work better because there's like more signal, I guess, to learn from. So I think that research you described sounds interesting to be like, why is that happening really? And what can you do about it? And how do you get the best of both worlds?
And perhaps perhaps if we could have gone further, well, probably. So, more commercial if I can.
Please.
So I'm open to collaborations, people. So if there are people who would like to take some of my ideas further.
And you will find Leslie on the fast.ai forums.fast.ai. He's got a number of threads saying like, hey, folks, come work with me on these interesting problems or tell me about your interesting problems. So maybe that would be one good place to find you and talk to you. And one good reason to talk to Leslie there rather than just over email would be that other people like me, for instance, could jump in and say like, oh, actually, I tried that and found these things, but didn't go around to writing them down. And it can be quite nice to have some early discussion in a more public place and then kind of dig into detail privately later, perhaps.
I suppose if I was being politically correct, I wouldn't say this, but my life is, I kind of treat my life as experiments too. So one of my experiments is, what if I started on the forum, I started a post on doing some research. And so I started a post, I put it up, and the idea in terms of doing layer-wise learning rates. Basically, I think that you're familiar with logs, of course. So I thought I could do better than logs. I know how it works, and I have many reasons to believe that layer-wise learning rates could be valuable.
Right.
So I started.
So LARS, that's L-A-R-S.
L-A-R-S. So I started a thread and suggested I laid out the ideas and suggested if anyone wants to do experiments, I'd be happy to collaborate.
We
And
have
nobody
a
did
question.
any
Okay, we'll come back. Sorry, go on. Yeah, so,
I'm done. Nobody did experiments, so I said, all right, that didn't work. But if there's people who really want to spend the time to collaborate, I can willing to do that.
okay.
So, for both Jeremy and Leslie, one cycle involves scheduling learning rate and weight decay. I've seen examples of scheduling dropout to increase it over time. What else could we or should we explore scheduling?
I wanted to ask you that too.
Okay, so I'd like
take it
to
away.
start. Actually, one thing that was, so at the ML conference I was at.
Is your microphone still working? Is the
What?
It's not. Okay.
Can you hear me? Did I break this?
Let's switch and I'll fix that up.
Okay.
Not our best technology day today. It sounds like it's working. Test. It's terrible.
Okay, can you hear me in China? Yeah. Well, maybe not China. India, whatever. Okay, so there was a speaker at the conference today, the ML conference, who talked about AI and neuroscience. And she said one of the things that is different between neuroscience, or the way the brain works, and the way artificial neural networks, is that the brain is very dynamic. One of the things I like, and I keep looking at, is how can we make things more dynamic in terms of neural networks. I looked at learning rates. Before this, I was in Germany. My more recent experiments have been with a dynamic weight decay, and I found that weight decay if you make weight decay dynamic, independent of learning rates, that it actually is advantageous in training difficult cases like large batch training. I suggested, I think that Jeremy and I are doing a collaboration, a dynamic data augmentation. So I think I think there's a lot of things that could be dynamic. You asked about curriculum dropout. Well, somebody asked. I'm pointing at you because you have the mic. Curriculum dropout is a little bit, so for example, what I'm doing now is a little bit counterintuitive. Curriculum dropout says start with basically no dropout, and let it increase as you do the training. So you're starting with no regularization and increasing it. My experiments now with weight decay. Weight decay is like one of the oldest regularization techniques where kind of everybody does and ignores. And I'm trying to shine light on weight decay, and hopefully that paper will be coming out. So I start with actually, in the beginning of training, I'm starting with a very large weight decay, and I'm decaying it separate from learning rate. And I end the training with actually zero weight decay. And I'm finding that, so that brings up that's odd, that's weird thing, because why would one form of regularization, weight decay, you want to decay it, and another form of regularization, dropout, you want to increase it? So it's, one thing seems to lead to more questions. So one of the questions that I have going on now is, what should you do with all forms of regularization, such as dropout and weight decay? I guess data augmentation is also, actually, we're talking about dynamic data augmentation. My idea there is a little bit like regularization I'm doing with weight decay. We start aggressively with data augmentation. And as we go on with the training, we end up with just the pure training data.
So let's just, is this one working now, or? It is, okay. And I'll just get you to just pull that away from your mouth a little bit. Just stand that like that. Let's try that. Because it gets a bit of air coming through. Okay, thanks. So let's pick that apart a little bit, because I do want to dig into this. And so if there are interesting questions, just hold on to them and don't let them disappear. Because I've been looking into this too, as you know. And one of the things that we have been, so changing stuff while you're training is amazingly awesome. and hardly anybody looks into it. And so, like, we did something really dumb and obvious and won a competition as a result. And the really dumb and obvious thing we did was say, hey, let's start training with small pictures and then gradually make them bigger. And one of the reasons that maybe people weren't doing this really dumb and obvious thing was because most models that are kind of built into libraries do something really stupid, which is they have their max pooling layer at the end of the convolutional section be a fixed size, right? It's like a 7 by 7 max pool, whereas most things support like what's called either global or adaptive pooling, which is basically pool as much as necessary to make a 1 by 1 cell. So if you use the fast.ai library, it'll automatically convert models to the adaptive form, and then you can use them for any size input. You start small, which means you can train 100 times faster, literally if you start with like 64 by 64, you gradually make them bigger. And also the cool thing is, every time you change the size of an image or something like that, you're giving the model different stuff to look at. So kind of overfitting almost disappears, right? Because you can't overfit to something that was a totally different image. You can only see the semantics of what's there. So like changing image size is cool. And then data augmentation, we changed it too in this competition. And the reason we changed it was just because intuitively I thought at inference time, it's going to be seeing full size, full resolution pictures. And the default ImageNet data augmentation is literally to take as little as 8% of the image, like a tiny fraction, and zoom into it. Like it does that. That's the maximum zoom it'll do. And I thought none of the pictures that it actually has to use at inference time are going to be that fuzzy. So as I trained, I gradually made the data augmentation less, so it had all the benefits of generalization of data augmentation, but at the end, the final weights are a set of weights that are particularly good at finding full resolution, non-fuzzy images. So to me, this is like one of the things I'm interested in is just make sure that by the end of training, you're presenting images that look like what you expect. And so one of the cool things we did also with the resizing was we didn't stop at 224 by 224, but we kept going, right? So by the end of training, we were actually training with bigger images than most people train with. So there's a couple of things you can fiddle around with.
So actually, it's your fault that I kind of, because you sent me an email, you said maybe we can collaborate on a paper on progressive resizing. And I said, well, that was your work. What value would I add? But you kind of got me thinking. And once you made the mistake of saying collaborate, it got me thinking about it. So I said, well, how do we take the basic idea, the abstract idea that's in progressive resizing and make it more general? And that's what I think the dynamic data augmentation is about. It's taking that idea in terms of starting, what's abstract there. So to me, I think that networks networks are blank slates. They have to learn everything. They have to learn that if you change the brightness, or you change the contrast, it doesn't matter. So if you can do very aggressive, and I even think you can save time by, rather than have a whole training data set, take a small subset of it. And take the small subset and then do very aggressive data augmentation where you change everything. So it can learn early on, well, these things are non-discriminatory. These are, won't tell me which classes.
And this is one of the reasons that transfer learning works better than people expect between vastly disparate domains. So like at Analytic, we transfer, and this today is really common, we transfer learn from ImageNet to 3D CT scans of the lung, which, at the time seemed like a really weird thing to do. But the reason it's not that weird is because at least the pre-trained ImageNet network has learned about ideas like, edges of things tend to matter, and brightness changes don't matter too much except in certain situations. Like it seems to learn a certain amount about just how pictures behave. And it's similar to what we then found with transfer learning in NLP. All the NLP folks I spoke to said, don't bother building a language model from Wikipedia because very little text that you use in real life looks like Wikipedia. So a language model, as you know, is a model that predicts the next word of a string. And so our entire thing was founded on the idea of building a language model on Wikipedia. Because it's the same idea, that if you can learn enough about English to figure out what the next word of Wikipedia is, you've actually learned a whole lot about language. And so you then look at tweets full of emojis. Most of the stuff you learn about how language works is still useful, because people forget how a neural network with random weights knows nothing about anything.
Exactly. It's a blank slate, you have to learn everything.
Yeah.
And transfer learning, I mean, basically what I'm trying to do is, what's the quickest way to train a network so that it's good for transfer learning? And and these are things like data augmentation, the progressive resizing, the subsampling, all these things can be used. And then, we're not actually doing transfer learning because then we're going to continue to dynamically change how we augment, so we don't do any augmentation at all at the end. But what's the question I'm asking is, what's the fastest way to train a network on maybe even limited data to become basically like transfer learning?
So let me ask one more question before we go back to the online questions. You mentioned curriculum learning. So curriculum learning, just to clarify, this is like a particular kind of dynamic learning where conceptually you're starting with an easier question and you gradually make it harder. So curriculum learning conceptually would be like start with less data augmentation, or start with less dropout, or start with a subset of classes or whatever. And this is where I get totally confused, because I guess I haven't found that many situations where this kind of curriculum learning concept seems to be that useful. The idea of like starting simpler, but it does feel like a lot of these things should kind of have some kind of U shape where you like start with like less data augmentation, maybe then you can then use higher learning rates or something, and then gradually in the middle of training have lots of data augmentation because that's where you care a lot about overfitting, and then at the end you trail off a little bit. Do you kind of have a feeling that some of these, or these kind of dynamic techniques should have this kind of U shape to them?
I do. Actually, in my superconvergence paper, I thought it was, to me, a nice insight. I think that one cycle is a combination, beginning of curriculum learning, because you start with a low learning rate, where it's easy to train, and you kind of jumpstart things, you bootstrap it, and then it gets harder and harder. And then once you hit the peak, then you do simulated annealing, and you bring the learning rate down. So I do think that curriculum learning does have its place. Sometimes you may want, I've seen cases where you might want to start with easier. Matter of fact, I think one of the speakers today at the ML conference said that they were working with words and started with short words. And then they went to...
Yeah, no, I think what I'm really saying is I think this is something I haven't spent enough time working on it. I think it just makes a lot of sense. And because in the end, we're about like getting that learning rate higher earlier, train more quickly. The other nice thing about high learning rates, of course, is less epochs through the data means less opportunity to memorize it, so less problems with generalization. I think that's super interesting.
You have a question?
We do. So how do you deal? Sorry.
Wow.
Okay, everybody go home.
Test it.
Okay, I can say the last.
Hold it close to yourself.
How do you deal with hyperparameter search spaces when you're not just picking a value, but also a schedule? Oh, did you hear it? Okay.
So I can try repeating it.
Please.
I'll paraphrase. I'm sorry. Actually, I missed it. I would have done that. how do you deal with hyperparameter again?
With hyper.
Okay, I think we're back.
Hi, testing. Yeah. So how do you deal with hyperparameter search spaces when you're not just picking a value, but also a schedule?
Oh, yeah. So I mean, I guess in a sense, there's more hyperparameters to pick now. You're not just picking a learning rate, but what's the difference between the lowest and the highest? If you're doing the stuff we do a lot of stuff with discriminative learning rates, so different learning rates for each layer. Then you don't just have a dropout, but it's, how fast does it increase? What's the highest? What's the lowest? Yeah, is this going to create an explosion of numbers to put in the wrong place, and now your model doesn't train anymore?
So I wish I had sage advice, but I think what I'm going to say is I try a lot of different things because intuition in terms of what would work. So and then the cyclical learning rate kind of came out of that. Right now, I'm looking at weight decay, as I mentioned, and the idea that weight decay right now is on the same schedule as I wish I had an equation to show you. So if you can imagine in your mind's eye that the equation for updating weights, it's going to be the learning rate times the gradient of the loss function. But then if you have weight decay, you're actually going to multiply the old weights by 1 minus the weight decay factor. That weight decay factor is multiplied by the learning rate.
Can I just do a quick summary for those that haven't watched the fast.ai course recently and might have forgotten? The Adam W. paper is one of the most useful to get a reminder of what Leslie's talking about here. But most of us, when we think about weight decay, we're not actually thinking about weight decay. We're thinking about L2 regularization, which is we take the loss function and we add to it the sum of squares of the weights, okay? And then we multiply that by some factor, which you were calling lambda in the equation you showed me earlier.
Well, lambda was the weight decay coefficient, but it's also multiplied.
Yeah. So let's call it lambda, and when you take the gradient of that, then you just get 2 lambda w, because you started with lambda w squared. And so originally, weight decay, the reason it's called weight decay is because we didn't add the square of the weights to the loss, but instead we actually directly subtracted lambda w from the gradients.
So the old weights are reduced by a little bit.
Yeah. And then so the important thing that Leslie's pointing out is that we don't directly subtract lambda w from the weights, but we actually subtract the learning rate times lambda w from the weights, right? So this is kind of the key insight here is like, oh, it's not really lambda at all, it's lambda times the learning rate, and this is something which I don't think anybody's really investigated until now.
I have not seen much. I mean, weight decay's been around for a long time, but I haven't seen anyone really shine a light on it. So I'm planning to shine a light on it because I was asking a question in terms of we have 2 entities in the update of the weights that are affected by the learning rate schedule. One is the gradients, which everybody says, well, the reason why we have to reduce the learning rate at the end is because the gradients have to be small, so we can find the minimum and all that good stuff. But I said, well, really, is it dependent is the schedule more important for the gradient part or for the weight decay part? And so I started doing some experiments, and my experiments are showing me that it's actually more useful to have a separate schedule for weight decay than just have it hiding behind the schedule for the learning.
So, this is interesting. I mean, so it makes sense. Like, why should these 2 things be tied together? Why? And I've thought about this a lot. This question, like weight decay, it pops up all over the place. Like another example is in NLP or anything where you have an embedding matrix. The weight decay is decaying the weights of the embedding matrix, even for words that you maybe never see. It's like there's a lot of interesting factors about it. Or if you're using like Adam, then this, I guess, was the LMW paper, was like the things that change the learning rate also change the weight decay. There's a whole lot of stuff going on. And then, so that brings me back to this question about setting hyperparameters when there are more hyperparameters to set suddenly. And my way of looking at this is those hyperparameters were always there. You were just setting them all to 1. You know, like if you just left it the same, like if you have the same learning rate at every layer, you have decided to use a discriminative multiplier of 1. If you use the same learning rate, you know, in every epoch, you're using an annealing factor of 1. Like, just because you didn't set it, or just because your software doesn't give you the parameter to tune, doesn't mean it doesn't exist. So to me, it's like, you're not adding more complexity. You're just becoming aware of the complexity that was there the whole time. And so, yeah, you may as well try other things, but try to do it with grid search is going to be insane. Like the only way to do it, it's a combination of intuition, but also realizing most of these parameters don't influence each other too much. So like, I'll give an example. For discriminative learning rates, I was trying to figure out, like, how, as I go back through the network, how much should I reduce the learning rate by for the earlier layers? And so I did a kind of a one-off hyperparameter search. I tried lots of different values. I actually used Frank Cutter's SMAC approach to kind of try lots of different parameters. And I ended up with lots of values of lots of parameters and how accurate was my language model at the end. And then I went back and I kind of looked at the partial dependence plot of a random forest, where the predictors of the random forest were the various hyperparameters, and the dependent variable was how accurate was my language model. And I discovered that pretty much universally, the value 2.6 is the correct amount to divide the learning rate by from layer group to layer group. So now, when I teach my course, I have this number 2.6, and people are like, why 2.6? It's like, well, it's the right number, you know. And so we found a similar thing with actually LMW makes life a lot easier. Like we found like weight decays, if you do just use a single weight decay, a value of between 0.01 and 0.1 nearly always gives great results. We try to find these rules of thumb, I guess, which then you kind of have less things to search through.
Right, no, I do too. I don't think I answered the question on that. So I'm kind of just going to.
That's okay. She was asking how is it different when you have to choose only one hyperparameter, right? Versus a schedule, and you need to know the maximum and the minimum, right? Or intermediate values.
Yeah.
I think we're close enough. Yeah. That's what else we got here. I can look here. So, oh, this is a great one. How could transfer learning be used for tabular data in business use cases like sales forecasting? I can take this one, and you can tell me if you've got anything to add. We just actually did the start of the tabular data for the new course lesson yesterday, so this is very much on my mind. So I actually did a lot of experiments about a year ago on deep learning for tabular data, and there's a lot of like things that you can tweak around, like where do you put batch norm and where do you put embeddings, but basically for tabular data, you've got a bunch of columns that are categorical, you know, like zip code or sex or marital status, and you've got a bunch of columns that are continuous, you know, like income or age or, you know, longitude and latitude. And so you do the obvious thing, the categorical columns, you create an embedding matrix for each one, and for the continuous variables, you have a choice. You can either just treat them as a direct input to the neural net, or you can put them into buckets and use a embedding for those as well. So something that a lot of companies are now doing and realizing is that when you train one of those models, the categorical variables, those embeddings, you can reuse them in your company, and you should. You know, so if you've got some model that's forecasting milk sales, and you've now got a set of embeddings for each store in your network, then you should totally use that same embedding matrix as the starting point when you train a model for shoe sales. Because the kinds of things that impacted, which people tend to buy more of that thing on Sundays versus Mondays in this place versus that place, are going to be some subset of the same things that impact their shoe buying as well. So, I mean, I think that's basically the trick, right? Is transfer learning. I'm sure there's more you can do than that. Like definitely with NLP, we've moved from just pre-training the first layer of embeddings to pre-training the whole network. But for Tabular, I don't know. I think we're still at the point of just pre-training the first layer of embeddings and reusing those. Do you have anything to add to that, Leslie?
For now.
That's cool. Yeah.
So there's one for Leslie. As a researcher, what advice would you give to students of fast AI, most of whom are more inclined towards solving real-world problems and do not have a research mindset?
I would say to be willing to question everything that you get. In other words, you try, even when you think it's working, does everything make sense to you? Does that make sense? In other words, you may look like it's working correctly, but is it really? And so, I mean, I will do that. And if something, very often when I see results, I'll say that's not quite what I would expect, and that could be wrong. Or it could be that there's some bug in it. I know it's hard to believe that sometimes our code has bugs, but it does happen on occasion. So you need to not be willing to just take everything at face value. I think you should always take a look to make sure that everything, at least to you, makes sense.
And I mean, I don't think there's a big difference between research and, the stuff you do in business day to day, because hopefully, I mean, you've done a startup, I've done a startup, like you try to build a business, you're trying to, if you're doing a data-driven product or doing some data analysis, you're trying to do the same thing, which is to figure out, I don't know, how to predict something or optimize something. The approach is kind of the same, right? It's like come up with a problem that you're trying to solve, make some hypotheses about the possible answer, find some way to do some experiments. But I tend to think that people, somebody who spent much more time in industry than in research, I'm surprised by how extremely similar the research world is to everything I did before.
Another piece of advice I would also offer is when you start with something that you know the answer to. So one of the things I'll do if I see a paper I like and it makes the code available, I'll try and replicate the results of the paper. Even if you are trying to do a business problem where nobody's done that kind of business problem, but if you can find something to leverage, because the truth is, if you start from scratch, new data, new everything, it's going to be very hard to reinvent the wheel. If you can take something as close as possible to what you really want, start with replicating it, and then incrementally change things to your problem. And that, that's really kind of the way to or making small steps from something that works and you know what the answer is to where you want to get something that actually works.
So somebody's asked for a quick summary of what one cycle is. So sorry, we should have done it earlier. But basically, it's a combination of two of the things that Leslie kind of mentioned. So one is that if you gradually increase the learning rate for a while and then gradually decrease it for a while, you can get to higher learning rates. But a cool tweak that I actually meant to ask about is that not only do you do that, but at the same time that you're increasing the learning rate, you're also decreasing the momentum. And then as you decrease the learning rate, you increase the momentum. So at the start, you've got low learning rates and high momentum, and you also do at the end. And in the middle, you've got high learning rate and low momentum. And like, I'd actually wanted to ask you, like, this idea of having the two things going in two different directions, what was the intuition behind that? Was it just something you tried, or was it something you kind of felt like, oh, that feels like it ought to work?
So it was something I tried. I wasn't sure at first in terms of what momentum. So now I have, can I share an equation?
Yeah.
Let's see if I have an equation.
While you're looking for it, I'll just explain my intuition about the end process. Like, by the time you get to the end, you know, you're pretty close to the right answer. To me, the idea of like, well, I think we all probably appreciate that a low learning rate seems like a good idea. You don't want to be jumping around the answer. But the idea of a high momentum kind of makes sense to me, because when that learning rate's really small, if you keep going the same direction, then you probably need to keep going that direction, right? So the idea of like, but on the other hand, if you are bouncing around the solution, then the momentum's not really going to bother you. So to me, it's kind of intuitive that at least at the end of training, a high momentum can help and probably won't hurt.
And actually, there's a paper, let's see which paper it is by, I think it's Smith and Clark-Lee at Google. They actually have the something close to the equation I'm going to show you, and maybe you can share it, where the learning rate, so the learning rate times the weight decay. Can people see that?
I'm not sure.
I'm not sure.
No, it's a bit fuzzy.
There's an equation there. The learning rate times the weight decay.
Here it goes.
On top. And on the bottom is the total batch size times 1 minus the momentum. So that generally stays, in my experiments, they generally stay pretty constant. So as you can see, the learning rate's on top, and the momentum,
So you've got learning rate and weight decay on the top, and you've got batch size, and what's alpha?
And 1 minus alpha is the momentum.
Okay, alpha, and so batch size and alpha are on the bottom.
So
you're
as
saying,
learning rate changes, momentum should change in that direction.
Okay, so I think we know the learning rate divided by batch size.
Right.
Lots of people feel that ought to be roughly constant.
Right.
Maybe it's not as true as people thought.
Right.
And so where do these other bits come from, of having the weight decay on the top and momentum on the bottom? Where does that come from?
So actually, the paper, the Google paper I was mentioning, I think it's the one where they talk about increasing batch size instead of increasing the learning rate.
Yes.
I think that might be, they talk about this momentum term, so they feed into it. But nobody I've seen really put weight decay in it. But I think that
this is more an observation.
This is an observation. I think it's from practical perspective, it's very useful because let's say you're not sure what's the right combination, what's the optimal values for these, but you kind of find them in one setting. We'll say, okay, now I found what these values should be in one setting. What if I change something?
Somebody's been kind enough to write that equation in the chat, so well spotted. Thank you.
Hey, thanks, whoever did that. So it's helpful from a practical perspective because sometimes one setting of these hyperparameters could give a somewhat better performance than a different one. So, for example, at different batch sizes, for example, say you can, at larger batch sizes, you can train faster. So how can you change the other hyperparameters to be able to train the large?
Equation I love, right? With a startup that I'm advising at the moment, I've been having them that we're basically trying to figure out how to let people train neural nets through a GUI reliably, which means we have to set all the hyperparameters to people. And I've been saying to them, don't try and create fast grid searches. Instead, find these rules of thumb, which is like if this divided by this seems to always be the same. And once you find these rules of thumb, then you can embed that in your software library or your processes or whatever, and then you don't have to worry about it anymore. It's like, why bother the user with setting parameters where you can get something that's 99% of the way there, just by multiplying by 3 or something. Yeah.
So it's actually right. And I will call this a rule of thumb. It's approximate.
Yeah.
But it's a good rule of thumb in terms of if you want to change one to get to another one.
That's great.
It's very helpful.
That's great.
I have a question.
Yes, please.
So segueing off of both one
Come
cycle.
close over here so we can they can hear you. So yeah, Goes.
Related to both one cycle and choosing hyperparameters. So one thing I knew how to do with cyclical learning rates was find out how many epochs I want to train for by just keep doing cycles until it seems to have converged. And also, in your general hyperparameter search methodology, you suggest using the early results as kind of an indicator of how hyperparameter searches will go. But now with one cycle, I don't know how to do this anymore. I don't know how to choose how many epochs I should train for, and whether my early results in this like early ramp-up stage of my final results. Do you have fixes for this so that I can recover my ability to do things?
We get this question all the time, and I want to know the answer too. Thanks.
So it's a trade-off. I think the longer, how much? So let me ask you, how important is final performance versus speed? You know, I mean,
well, if I could put it another way, though, like for me, the place that keeps coming up is like, I got some data set, I've done some pre-processing, I want to train a model, and I think like, oh, I'll try 4 epochs. And I try 4 epochs, and it's still clearly underfitting.
Right.
And then, so the question I always have, and my students always have, is like, what do I do? Do I start another cycle from there? Or do I go back and now it's 2 cycle? Do I go back and start like, how do we do this in practice? You know, do we kind of go back and do a new cycle from scratch and try making it twice as long? Or do we keep training from where we are and now it's end cycle? Or
right, no, that is a good question. The reason it's a good question is because it almost seems like the total number of epochs should be, it sounds like a grid switch, and we know a grid switch is a nasty word. So what's a way to do it without a grid switch? I bet there's an answer to that. I don't know it right now. Give me a weekend.
Okay, I mean, I'll tell you, like my approach is like, I pretty much always keep training from wherever I got to, because to me it's like, yeah, why not, you know? And I'll tend to do that thing of like, I don't know, I'll like halve the maximum learning rate and do another 4 epochs. Exactly. And so this isn't like intentional, it's just because like, oh, I undercooked, you know, I did less epochs than I probably should have. So, you know, I don't want to wait and go back to the start. I've got some decent weights, let's keep going. Works fine. On the other hand, if I overcook it and start off too many epochs, then you kind of have to go back and start again, because particularly with one cycle, it's if you go too high, I've noticed you can really kill the validation loss. So I tend to try to do a few less epochs than I expect and chuck on a few more if I need to.
The one way to find that I find is really useful in terms of trying to say, oh, no one go past that. But what you're saying now in terms of like the SGR, that could very well be a good way to handle it in terms of if you don't know what, how many epochs.
Can I ask you something though? Like, I mean, okay, so the learning rate finder, at least with random, when you start with random weights, you kind of get this shape, right? Yeah. And you kind of, I tend to look for the steepest gradient, or Sylvain, who is a researcher in residence, his approach is find the bottom and then go back 1 order of magnitude. Those 2 values tend to be about the same, I've noticed. The thing I find though is if you go a bit higher than that, so it's still clearly decreasing in the learning rate finder, I very often find this weird thing happens where my training loss does actually get pretty good, but my validation loss can be like way off. You know, there's this weird thing that seems to happen where with one cycle, if you just go a little bit too high, have you noticed that yourself? Or? No, okay.
So hard to address it, but let's see. So this is the kind of situation I come up with I work all the time, where someone's screwed, and I have to try and think. So one of the things that is useful for people to do is to think. So when you come across, so why would the validation accuracy be hurt so much? Let's think about it.
We have another question here.
Sounds like it. Yes.
So regarding the paper, accurate mini batch SGD, training ImageNet in 1 hour.
It's good paper.
Yeah, Priya Goyal.
I like that.
Yeah.
So he says it's full of little tricks.
Yeah.
And he's asking, what are your favorites? And what do you think is something that we should know, but many are still not aware of, that makes training really easier?
I got one straight away. I can do it. Okay, I've got lots of favorites in that paper. That's Goyal, Goyal, Priya Goyal, who I think might be now on Facebook. And they can't hear your mic still, so I might have to give you this one.
I can speak up.
Okay, please speak up then.
Yeah, show the paper.
Yeah, please. Let's show the paper.
Have it with me.
Accurate, large, mini batch training in 1 hour. Come on, focus. You can do it. There we go. So one of the ones I like, which is actually kind of hidden away, is in a ResNet block. So in a ResNet block, you've kind of got one path which has some convolutions and one path that has an identity. And in the path of convolutions, you've got also batch norm, right? And so there's one cool trick in the Goyal paper, which is take that last batch norm layer, which has 2 parameters, right? There's the amount that you multiply by and the amount that you subtract. And they're learnable parameters. And the Goyal paper, they say initialize the learnable multiplication to 0. And so what that means is that all of your ResNet blocks initially are literally identity blocks, right? Because the final batch norm is multiplying the non-identity path by 0, so it disappears.
If I can interrupt,
please.
That's curriculum learning. It's really a form of, can you see it? Because what it's going to do is going to do mostly skipping, and it's in a way allowing the network to train more easily.
Okay, so I'm not saying right or wrong, but for me, when I think curriculum learning, I think like changing the data in a way to make it easy, but to change the model to make it easy, that's great. And so, yeah, and so this lets you, and so here's the reason you should care about these large batch size papers, even if you don't need to train on 500 GPUs at once like Facebook does. All of the things that let you use large batch sizes also let you use large learning rates. And so this is something that a lot of people, I don't know that I've even seen anybody mention this in a paper or a researcher agenda or anything, but all of these tricks that let you use a big batch size, the reason they're important is because you don't get many batches, right? If you've got a huge batch size, then one epoch doesn't have many batches. So you've got to use that batch to jump a long way, right? So all of these tricks that let you use big batch sizes also let you use large learning rates and therefore let you train faster and generalize better. So it is really worth studying these things like KFAC and LARS and this batch non-zero trick. I don't know if that's a name. Another trick from, I think it's from this paper, was it's called ResNet scaling or ResBlock scaling, which is basically you take the convolutional path, the residual path, and you scale it down by like 10. It's full of these little tricks. You got any more favorites from that paper?
So I will say that that paper talked about weight decay and pointed out that weight decay is affected by the learning rate schedule. And that was one of the ingredients that led me to work at the decay. So that's a recent favorite. So I like that.
So I feel like we should wrap up because we've taken you more time.
Can I just mention one other thing?
Yeah, I'd love to. That's what I was going to say. Let's wrap up with whatever you want to.
I do a lot of reading, and I have a new favorite paper.
Oh, good.
That is actually related to this stuff. Now I have to find the paper.
So somebody just added a comment. If there's one researcher everybody knows in the fast.ai community, it's Leslie Smith. And he's sitting next to me right now.
Oh, wow. Usually, anonymity was my middle name.
This is
so this is it. It's a new training tape. It's a new paper.
Wow, who knew Harvard University has deep learning researchers? How about that? Come on, focus. Yeah. Min norm training, MINN norm training. Maybe jot that down. So tell us about it.
So I will tell you just a little bit, because what they
And so
actually, if I can give you the archive number, 1806.00.
1806.00730. Thanks.
Anyway. They take ideas from support vector machines in terms of large margins.
3 people have already found it. Okay. We got it.
People have found it. All right. Well, anyway. So this part of the reason why is that it's related to the experiments that I've been doing.
Oh, this is the famous Sachs.
Andrew Sachs is famous.
Okay. That's Sachs.
Oh, okay, good. So I actually have been interested in large margin. You know what I mean by large margins? Or do you need to explain that?
Please do. I mean, I think I do, but I would.
Okay, so SVMs support vector machines. They're known as large margins, where it tries to maximize the margins between the different columns.
Yeah, and there's that hook loss or whatever it's called.
Sure.
No, okay, anyway, go on.
So this idea of max margins is, I don't think, has been really brought into deep learning world very well. But I think actually this paper is one of the first ones that I think does a good job. And one of the things that he compares, they offer a new method of doing optimization. And they say it's better than L2 regularization.
Mm-hmm.
And they have these figures in here where,
this one?
Yeah, this one. And they show that if you use a large value for basically L2 regularization, the weight decay value, that you can go quickly to the solution, but it's off. It's off the mark. That's the first one. On the other hand, if you're
looking at the paper, this is figure 3, and this is in B. There's a gap between the 2 lines.
And then they show that if you use a small value for the weight regularization, then you will train to the right value, but very slowly.
Okay, so this is C.
So I said to myself, well, why don't you start with a large one, get it enabled, and then use a small one?
Quite.
So that implies that there's a dynamic weight decay would be a good thing. And so I said, yes, this is actually some theoretical support for what I'm finding encouraging.
Okay, that's great. Well, I feel like I should wrap up with fireworks or something. But, did you have any questions or anything you wanted to close with?
I just want to close again by just thanking you for.
Oh, well, thank you.
I appreciate.
Thanks for coming. It's a long way to travel, and you were wondering, should I come to MLConf? And I said, you know, what if while you were here we had a chat? And you were like, okay, I'm in. So,
right.
we're very grateful.
To come.
All right. Thanks so much for coming.